Hi, everyone. Welcome back. It's once again my great pleasure to introduce the next speaker from the industry panel. It's Jeffrey Delmerico with the Microsoft Mixed Reality and AI Lab in Zurich. I had the great pleasure of working with Jeff when I was at Microsoft, and I'm really excited to see what new work he's going to show. So his work mostly focuses on bringing robots into Microsoft's mixed reality ecosystem and enabling human-robot interaction using MR. He has a PhD in computer science from SUNY Buffalo in 2013 and has done a variety of postdocs both in Zurich and in sunny Hawaii. So please, with that, please enjoy the talk.
Thank you very much for the introduction, Helen. I'm happy to be here and to talk to you a little bit about some work that we're doing at Microsoft in the space of, or the intersection of MR and robotics. And so the title of the talk is Spatial Intelligence and the Industrial Metaverse, and I'll gradually get to some definitions of both of those terms, which tend to be kind of vague these days and thrown around a lot. Sorry, I'm not, there we go. There's been a few different sort of shifts in the way that we do computing in the last couple of decades. So, and of course, the ones on the left are still around. We have kind of applications running on laptops that where the device doesn't have any sense of its space. We have applications that run on mobile devices that you might have like an outdoor location through GPS or some local spatial information, and you might have some of the services provided through the cloud, and more recently, and this is obviously why we're all here, we're exploring experiences that exist in mixed reality, where the computing happens on some kind of device. It might be worn on your head or held in your hand. In general, these sorts of experiences need to have a sense of the environment, of what the user is doing, and their location in space. And so when I talk about spatial intelligence, that's kind of where we're going with this, is that the device that is providing the experience needs to understand where it is and what's around it. Microsoft has a few different versions of the HoloLens 2, which is the most recent mixed reality device that we offer. And these go a bit towards the industrial use cases that they're kind of marketed for. So in the center, sort of a clean room designed HoloLens, and on the right, there's one that's integrated with the hard hat, so it could be used on construction sites. And so when we talk about industrial metaverse, we're looking at targeting use cases that exist in the industrial domain, factories, warehouses, and so on, with frontline workers using HoloLens, and not as much for personal or commercial applications. At least that's the focus based on this talk. So I'll talk a little bit about a couple capabilities of HoloLens 2 and mixed reality in general. Sorry for the lag. Doesn't look like that on my screen. We want to be able to provide an immersive experience for the user. And in all of these cases, there's people, doing their jobs better or more efficiently, or more, with better information based on their ability to access mixed reality experiences while they're doing it. And there are a couple of services that are offered in conjunction with HoloLens 2 that help to actually accomplish real-world tasks. So one of them is called Remote Assist, where you can essentially make an interactive Skype call with someone, and they can view your first-person perspective from the HoloLens, and then annotate things that you can see as holograms in the real world. So there's a bit of sense of space so that the remote person can mark things that you can then use to do your job better. There's another service called Guides, which is essentially a mixed reality training tool. So these MR experiences can be designed where the user walks through a set of instructions, learns how to do a task. This is actively used in training, for example, manufacturing workers to do some new step in the manufacturing process. And that needs a bit of local spatial information in order to provide those experiences to the user as far as what objects are nearby. And then lastly, there's Microsoft Mesh, which is to facilitate collaborative interactions in MR. So you could have people who are remote, people who are in virtual reality, people who are in person, all able to experience the same thing, again, in a local context. Now, up until now in this talk, you might be thinking this is a 15, 20-minute long advertisement for HoloLens, and I assure you it's not. We're getting there. All of these different services and experiences so far kind of operate in a local space. And to do real tasks in industrial environments, that's not sufficient. Room scale MR is not good enough to really improve the ability of frontline workers to do more and to do their jobs more efficiently. And so that brings us to the main idea of this talk is being able to provide spatial intelligence at larger scales. And so the team that I'm a part of in Zurich is focused on, we work mostly on a cloud service called Azure Spatial Anchors, which it provides mapping and localization from the cloud for different MR devices. So primarily HoloLens 2 and HoloLens 1, but also mobile devices. And in a research capacity, non-commercial, there's also a robotics compatible SDK that you can use to localize your ROS based robots to the same spatial anchors. And so this service essentially currently at a small scale, and in the results I'll show you here, when we talk about future research that we're doing into larger scale mapping and localization, the concepts are the same in terms of we want to localize different types of devices to the environment. And so what are the applications that this can be used for? First one is what this image is supposed to show. It's what's called contextual data access. So being able to move freely in your environment, if it's a factory, for example, and based on where you are and where your MR device can localize itself in that environment, call up relevant information and visualize it or interact with it. In this case, viewing maintenance history for a machine or something like that. Being able to interact with digital twins of the environment that live in the cloud or have spatial information stored in some other way and be able to interact with that. Indoor navigation, which is still sorely lacking in most, even in mobile devices. And finally, the reason we're all here is to be able to enable robots to use the same services for contextual data access and interaction with digital twins, and also indoor wayfinding and path planning, and human-robot interaction and collaboration. So that's the focus for the rest of this talk, is showing some of the kind of results in this direction. So to do all of that, we need large-scale maps. We're going to provide those services across an entire factory, an entire warehouse. So these are just a few examples of the large-scale maps that we're building and some sort of prototype capabilities. So This is like a 430,000 square foot or 40,000 square meter factory. Several supermarkets that are also thousands of square meters, multiple floors, a construction site. So there's some images in the bottom left where you can see it's a challenging environment with bare walls and and concrete everywhere, and here you can see same space. We've merged data from multiple different sources. So this is data from HoloLenses, Spot robot, and the camera's on a handheld LiDAR sensor. And you can see the different levels of the trajectories there. So the lowest one is the robot walking around about half a meter off the ground. There's another line of trajectories, and it'll repeat in a second. You can see it, where someone's holding the LiDAR scanner at about chest height. And then there's a bunch of different trajectories for people of different heights clumped together at the top. And so you can see we've been able to fuse all of this data from different modalities. Well, it's all the same, it's all visual features, but we're able to map collaboratively from a bunch of different sources, not just HoloLens. And we've also been exploring other, so dense maps that incorporate LiDAR and depth data, because on many of these platforms, including HoloLens and many robot platforms, you've also got range sensors on board. And if we can localize and map with your visual cameras, we also want to do the same with dense data, because that provides another representation of the environment. And so to give a high level overview of our ambition for what we want to do with these large scale maps, at least with respect to robot applications. So we really want to keep kind of all the different spatial data that we could imagine being useful in an industrial metaverse scenario, keep all of that aligned in a single representation in the cloud. And that includes, on top of the maps that we build, also being able to align external third-party digital twin data to that, like floor plans and BIM models. And we also want this to be accessible by all different types of devices that can localize themselves. So HoloLens, robots, mobile devices, maybe someday autonomous vehicles, because fundamentally they're all solving the same visual SLAM problems. So the rest of this talk is mostly some short videos showing cool stuff that we can do with these large scale maps that are relevant for not only industrial metaverse scenarios, but also for robotics research. And so localization and mapping, human-robot interaction, navigation, and interaction with digital twins, and all the different kind of layers of the map that we need for that. So first, this is just showing with one of the maps, like what I showed in the previous slides, we can localize different devices. So here, a couple of people walking with a HoloLens, as well as our Spot robot walking around in our office in Zurich. And normally we don't track where the devices are when they're using the service. This is just for visualization purposes that we're showing the trajectories. And once you can localize multiple different devices to the same coordinate system, then you kind of get human-robot interaction for free, because we can do spatial-based tasks or interaction like this. There's a mixed reality button there in the blue window that says, "Come here." And what happens is that because the HoloLens is localized to the map and the robot's localized to the map, when the user presses the "Come here" button, the robot can compute the navigation goal it needs to come to the user by setting a goal just in front of where the person's standing and planning its own trajectory to get there. To a more maybe useful industrial scenario, this is what we're calling mission planning, where in mixed reality, the user can place a series of waypoints that the robot should follow, possibly at a later time. The robot doesn't even need to be there during this stage. So the user can plan for example, inspection mission for the robot in advance using mixed reality. And then later on, the robot can wake up and then begin executing the mission autonomously. And so it will walk to the waypoints in sequence as they've been designed in MR and can execute some task at each one. For example, taking a picture or a LiDAR scan or executing some other action. And then the robot can finish executing the mission and go back and charge, for example. And when we have some external information, this is showing just a visualization of, if you have a dense mesh of your environment, you can visualize it with the HoloLens as like a digital twin representation. But you can imagine also that you have your localization map that the robot can use to know where it is in the environment. You could also have a digital twin like this, a dense map aligned to the sparse map that's used for localization, and then be able to allow the robot to utilize the dense representation for other tasks like manipulation, 3D path planning, and so on. The final capability I'll talk about is navigation. So this differs slightly from the mission planning scenario. It's going to look kind of similar, but this kind of augments what we showed before. This is a Unity application where the user doesn't even need to be on site, but we can plan another mission for the robot. But this time we leverage the sparse map to do path planning. So essentially, you can see there's some gray lines in the map, and there's black dots for feature points. There's a service running that uses the trajectories that were used to build the map to infer which paths might be traversable. And so when the user chooses some waypoints that they want the robot to walk to, we can compute a sequence of intermediate waypoints to provide a global path for the robot to follow. And essentially, we break down that entire trajectory, which is 3 high-level waypoints where the robot should do some action, like here at the fire extinguisher, and we break down those blue lines into smaller 1 to 2 meter trajectories. So we rely on the robot to do local obstacle avoidance and path planning. It doesn't ever have to know the full map to do this. It just provides a start location and a goal location, and the navigation service figures out the path that it should follow. And we leverage that here to do, again, an inspection type mission. And this is a full one that starts from the dock, ends at the dock. The robot can be told to execute this remotely. And that's like a more realistic industrial scenario. And finally, the exact same navigation service can be used for indoor wayfinding for people, because as a person wearing a HoloLens or looking at a mobile phone, you can walk without colliding with things 1 or 2 meters. And so we can provide the same intermediate waypoints to get you from a start location to a goal location with a HoloLens. Thank you very much for your time. I'm happy to answer any questions if there is time. Otherwise, we'll have the panel discussion in a little bit, and I'll be happy to talk more about this stuff then.
I think we have time for one quick question. So I don't know if you want to take the one from Gabor on.
That's a good question. Yes. So the ARM64 support is it's unlikely to be backported to the current version of ASA, but we're trying to have better platform support in future products. I can't say more than that, but it's on our minds for sure. And yeah, thank you for requesting that again. That helps me to have some motivation to push for that internally.
Hi, I have a quick question. So you're using those anchors, spatial anchors, based on localization. I'm guessing you're using some sort of localization frameworks from a SLAM-derived map, right? So what happens to user perception when you encounter like a loop closure during mapping? Does that make people dizzy? Is there any impact on user experience when that happens?
So we, at least with the results I showed here, we do the mapping and localization in separate phases. So in more of a curation type scenario. So the way that this is intended to work is that you would do a capture of your environment. It doesn't have to be exhaustive. You can incrementally update the map. It's not intended as a real-time SLAM system, if you understand. So like you don't experience any loop closures. There might be wormholes in your map, in which case you might get disoriented if the MR experience is built on top of the map changes. But that's the piece we as a team are actively working to prevent, is that we want to make the most consistent maps that we can that reflect the actual state of the environment. And that actually comes up. There was another question about dynamic environments, which is relevant kind of to this question. And so again, we kind of do the mapping and localization in different phases. So we don't, the ability to update the map is relevant for both dynamic environments and cases where if you have a wormhole in your environment, you can add more data later and hopefully resolve that so that you get a proper loop closure. But we're not addressing the case where we're tracking dynamic objects or dealing with things that are moving too actively in the environment.
Thank you.
All right. Thanks so much, Jeff. Thanks for the presentation and the answers. I'd recommend that we take the rest of the questions during the panel discussion. So thank you very much. And let's thank the speaker again.